Swayam Prabha. Digital India. Educated India.
Potential you said we can measure it with respect to a reference. Is this like the metal reactivity series?
Yeah, same thing I'm saying. Given metal electrode, suppose if I have a zinc dipped in zinc sulfate, what is its potential with respect to an hydrogen electrode? Hydrogen electrode potential I arbitrarily define 0. So from there how far this is? This is at a distance of minus 0.76 volt. If something having negative sign compared to the hydrogen electrode or negative compared to the hydrogen electrode, that will be a very good anode material in a spontaneous process. See, a material can be anode and cathode, electrode-electrode interface can be anode and cathode depending upon whether it is an electrolytic process or galvanic process. But I am now talking about for a spontaneous process. In a spontaneous condition, compared to the hydrogen electrode interface potential, if there is a potential which is more negative, that means that interface will be a very good anode. So if I combine zinc in zinc sulfate with hydrogen in a 1 molar HCl as an cell, then what will happen? Zinc will oxidize, hydrogen gas will evolve. That means proton reduces, zinc oxidizes. Suppose I look at copper sulfate solution interface, 1 molar standard condition, whose potential is plus 0.34 with respect to hydrogen electrode. That means in normal, in spontaneous condition or in galvanic condition, your hydrogen will oxidize to proton, that electron will go to reduce copper 2 plus to copper. So now between zinc, hydrogen and copper in standard condition, what is the reactivity series? Which is more reactive? Zinc sulfate, then hydrogen HCl, then copper sulfate. So you got a reactivity series for a given interface. It is the same thing what you did in 10th standard, little differently we are doing now. Clear?
Yes. So why have you chosen hydrogen to be the standard?
You can change the standard. Who told you not to change? Oh. I can have any standard, right? In fact, I will show some example where people, maybe tomorrow, where people who work on lithium ion battery, they will not use hydrogen electrode. Why? In a battery, in building an hydrogen electrode is difficult. So we need to have something inside the battery to act as a reference. So I need to create a pseudo reference. Okay? There what they will do is they will use lithium metal as a reference. So define lithium metal as 0. If I define lithium metal is 0, hydrogen no longer 0.
Yes, sir.
Hydrogen will gain some value now.
Yes, sir.
So answer to your question, not necessary you have to have hydrogen as reference. You choose anything you want as reference. But all of them has to be listed against that reference. So that you form a electrochemical series, same series with different numbers. But the reactivity will not change. Because you change the reference, zinc will now become less reactive? No. Accordingly, the numbers only will change, but the series will remain as the same series. The most reactive one will be in the top, least reactive only in the bottom. Whatever may be the numbers you put here, that will not change. But it is up to you, you can change. Any other question?
So like for metal, it's called Fermi level, right? For electrolytes, redox, what is it called?
We will do it. Yeah, redox means.
What are the names?
What is it called? Fermi level, it's for metal, sir. So what do we call it for?
Okay. So suppose I have say zinc ion in the solution. How is the zinc ion present in the solution? If it is an aqueous solution, neutral condition, say zinc sulfate or something. What is the form in which zinc ion present? Sodium chloride you take, put it in water. What is the form in which sodium plus? Sodium ions. Na plus? No. It's a form, species. What does that aqueous mean there?
Solvate.
So the ion not independently sitting there. It has got ligands around it.
Yes, sir.
So when you have ligands around it, we use, I think again in the second year you will study something called CFT theory. Crystal field stabilization. Water.
No, ligand.
Ligands.
What is that?
Ligand is again another species which is coordinating with your ion. So if you put sodium chloride in water, why sodium chloride breaks up? Because the interaction between the water molecule and the sodium stronger than the sodium and chloride. Lattice energy is overcome. That you have studied in thermodynamics, same thing. But when lattice energy overcome, what is happening? There is an interaction between the water and your ion. If that interaction disappears, again sodium chloride will form. So that means it is persistent. So what is binding tightly between the sodium, the force that is binding tightly sodium and the water. Okay. So that will lead to some new species. What is that species? You see Na plus surrounded by few water molecules. Okay. So those molecules which are surrounding this metal ion is called ligands. In coordination chemistry, in the second year you will study ligands. Okay. So Werner complex, all that you will study in the second year. Okay. That's why I asked you when I came, what you know, what you don't know, I wanted to find out. Ligands probably you will get used to it in the coming months. Okay. So now what happens, you will also study something called CFT theory. Suppose I have a transition element, it has got a 3D transition element. So it has got some electrons in the 3D orbital, right? Okay. Now that ion, transition element ion, that is, now I am going to put it in water, say ion, okay, ion 2 plus or ion 3 plus, okay. So what will happen? If you have only that ion in the gas phase, all the d orbitals, 3D orbitals, there are 5 of them, right? All of them are identical. Electron can choose anything. It can go to dxy, dyz, dzx, x square, y square, z square. Now imagine you are going to put that ion in a solution where the other ligands are there. Ligands are having their own electrons. Now this electron comes and meets the electron in your metal ion. Then what they will do? They will repel. Or they will form bond, or they will repel. Something will happen, correct? So now the atmosphere around the ion is no longer symmetric. No longer symmetric. What does it mean? Earlier when the ion is in the gas phase, any angle you look at from that ion, it was the same. Now imagine there are 4 water molecules parked like this. Now you are the ion. You look down, you see there is a water molecule. You look up, you see nothing. You look this side, you see 2 water molecules. So the ambience around the ion become asymmetric. So that means the ion faces different forces from the different direction because of the repulsion between this electron and the electron in the ligand. As a result, your d orbitals which was originally degenerate will now become non-degenerate. The orbitals which face the ligand will split, will have a different energy than the orbitals which does not see any ligand. So you will lift the degeneracy, a non-degeneracy will come into the system, okay. Because of that, some d orbitals move, stabilize, will go lower in energy, some d orbitals will go up, will go higher in energy. So net energy change must be constant, should not be changing, right. So you will see there is a barrier center, from there some go down, some go up. Okay, you will see that CFT theory in the coming years. So now, what is the, suppose you have an orbital which is empty, which is supposed to going to receive electron. Okay, so what is the energy of that orbital which is going to receive the electron? Okay, what is the energy of that orbital in the given environment which is going to receive that electron? That energy is redox energy, where that orbital is positioned in energy level, absolute energy level, compared to the other material which is in the solution where it is placed. That is the redox energy. So from that level, electron may come out if there is an oxidation of the electrolyte. To that level, electron may enter if there is a reduction of the electrolyte. Again, whether it will come out or go, electron will go in, depends on what is the activation energy involved in that process. Okay. There are 2 chances, an ion can get reduced also, oxidized also, which one it will prefer? It will prefer a method where activation energy is low. Correct, no? So this is redox energy. So in a simple way, the orbital of that species in the solution, that is metal ion surrounded by the solvent species, that species in the solution, the energy level of the virtual orbital there which is supposed to receive electron, that is your redox energy, which we are comparing against the Fermi level to understand whether electron flow this way or electron flow this way.
So if you have a particular species like say Na plus, do you know how exactly the ligands will arrange themselves around Na plus, or is it?
There are some studies you can do.
So to exactly how they'll arrange. Okay. So every
How many? We call it as a ion dipole interaction. How many dipoles will be around each ion you can know. We call salvation number.
Would I know the positions?
See the position, you see when you have something in the solution space, always there will be a vibration between these two entities. So position is not fixed always. Depending on what temperature, what solution concentration, it will have something. So I can give you a time averaged position. If you ask me at this instant where it is, is very difficult. Right? Suppose it's like this. If you take a crowd which is highly non-synchronous, this is a crowd. I am asking you to do some exercise. Do this, do this, do this. When you may be doing this, C may be at the time doing this, C may be at the time doing this, another person doing this. So now you are keep doing it. Then from the aerial view, I take a photograph. Okay? That's called time averaged photograph. What it happens? The number of people who are raising their hands up, number of people who are having the hands this way, number of people having the hands this way, number of people kneeling, that may be roughly the same. But in one photograph, your hands will be up. In the next photograph, your hands down. But at the same time, someone's hand went up. So the time average I can tell you. But if you tell exactly what is the photograph means, it's difficult. For that, at that instant, you should have a technology which maps at that instant. But why you need that? Because we always want what is the time averaged behavior. That instant behavior we don't need. Correct? No? I mean, you need in some measurements, not here. Because here, when you talk about battery, you are not talking about single atom. Avogadro number of atoms are there in the electrolyte, Avogadro number of atoms are there in the electrode, Avogadro number of, reactions, moles of, reactant is converted into product, right? So it is collection of atoms or particles only we are looking at here, not one single. Therefore, it doesn't matter how at that instant it looks.
Yes, sir.
Any other question? No? So, are we going to have a break between two class or it is going to continuation, madam? No. If you have arranged some what do you call tea, coffee, no means? At 11, Then I will continue. Okay. Shall we continue or? Okay. Okay. So, now what I am going to teach you with some slides, how people constructed that, researcher constructed that electrochemical series, which is there in your textbook, how they have constructed it without doing electrochemistry. Okay, that means they have come to that series using only thermodynamics data. How we do that, you will see in a minute. This is electrochemical series, okay, one second. This is electrochemical series. I am going to explain you how to construct this, okay. Yeah. Now your question is?
It's just a speculation, sir. Did that person measure it by using how negative delta G was? Was that how they did it, or did they do it another way, sir?
Always, if I report something, a measurement is done. Without measuring, how will you report a value?
No, sir. I'm saying, can they also measure the electrochemical series by just checking how negative the delta G is?
Yes.
Is that how they
Delta G is related to E cell. That's how it is done. That's why the example here. You see what is called Born-Haber cycle. Okay. So, for example, I have hydrogen. Okay. I have hydrogen in vacuum. It's a hydrogen molecule. I am going to break the HH bond. We call enthalpy of atomization. That takes you here. It's in the gas phase. Now, I am going to remove an electron from hydrogen atom. We called enthalpy of ionization. I take it there. You have to do it not with one hydrogen atom. I have got a number of hydrogens you have to take and do, so you get the average property. Now, I am going to drop this fellow into water. Then, it will get solvate. You get enthalpy of hydration. That comes here. Now, if I want to go from hydrogen in gas phase in contact with the liquid. That is what your standard hydrogen electrode does. Your hydrogen gas phase, there is a liquid, there is an equilibrium, and there is an electrode, right? From there, I want to go here. If I want to go from here to here, all I need to do is I add all the 3 values. These are all thermodynamic quantities. Or if I want to go from here to here, I will add these 3 and reverse the sign. Correct, no? You can do that. So now this is what is electrochemical series is. In electrochemical series, we will represent in the standard reduction form. That means a species in its oxidized form plus electron gives a reduced form. This is how we will write electrochemical series. Again, you have to follow an IPAC convention. So we are going to only report to standard reduction potential. Something in the oxidized form plus electron, its reduced form. That is standard reduction potential is what we are going to report. You understand? So now let us look at this. I want to get this value involved in this pink direction. Correct, no? Pink arrow direction, right? So now you can do that. If you do it, this comes about this much joules per mole, okay? So for the required reaction means you wanted to go this way. So sign change, okay? Here I am talking about 1 mole of hydrogen atom. That means the enthalpy of atomization, you have to divide by 2 to give it for 1 hydrogen atom, correct? You know that part. So after that is only hydrogen atom. So you can call 1 mole of hydrogen atom. So now you have this, yeah? Now if you divide by the Avogadro number, I did not do that. What I have done, I have converted kilojoules to electron volt, okay? Because I have this conversion, 1 electron volt is this many joules. And then I divide by Avogadro number, that tells you for energy involved 1 particle. 1 particle. What is that 1 particle here? Hydrogen atom. This is how much? Minus 4.45 electron volt per hydrogen particle. That is the energy which is evolved when H plus in aqueous medium takes an electron, goes to H. H plus aqueous goes to H. Half H2, because we are talking about molecule. So half H2, correct? So for that reaction, this is energy. Okay? Clear? But you know what is the energy involved in removing an electron from hydrogen atom from the atomic theory? Right, no? You have done in the first year, no? First year or second year, where hydrogen energy required to remove an electron from hydrogen 13.6 electron volt. Which year?
First year.
13.6 electron volt to remove the electron. That means to add the electron to H plus in gas phase. H plus in gas phase, if you add electron, how much energy will come out? Minus 13.6 electron. But I do the same reaction. I am getting only minus 4.45. So some energy is offset because of the hydration phenomena. So removing an electron from hydrogen is not same in gas phase and liquid phase.
Yes, sir.
In gas phase, you spend the entire energy to remove electron. But in liquid phase, you spend only small amount of energy. Why? Simultaneously, when you remove the electron, the proton formed is interacting with the water dipole, forms a H plus and hydration cell and liberates some energy. And that liberated energy is used in removing electron from the hydrogen. So the net energy you have to spend is now less than what is actual in the gas phase. Okay. So removing an electron from hydrogen is a very difficult task in a gas phase. It's easy task in liquid phase. Therefore, this hydrogen proton is not same in gas phase, same in liquid phase. They are different by this much of energy. Okay. So this is electron volt per particle for standard reduction reaction of proton into hydrogen, right? Same thing we do for lithium. You get minus 1.3 electron volt. Okay, minus 1.3 electron volt. Make sense? And how the delta G and the NFE are related? By a negative sign. Delta G is equal to minus NFE. So if I express them in terms of E value, they all become positive. minus 4.5 become plus, minus 1.3 become plus value. If I express them in the voltage, I have expressed in the energy form. Okay. Now, what I have done is a number line. 0 is there in the top. So, minus 1.3 is here. So, minus 4.5 here. 0 energy I attribute to the vacuum, for example. So, the energy required to remove an electron from lithium metal and put it in the vacuum, that is your, what is that energy? Ionization energy. But if it is a metal, you call it a work function. Okay. So, now for this guy you see, this is a kind of a work function. But this guy got lesser work function, this guy got more work function. Okay. So, now what I want to do, I want to make like this, I can do a Born-Haber cycle for any metal electrolyte interface, and then I start populating the values in the number line. Okay. Now, what I am going to do, I am going to assign arbitrarily for this guy the whatever the value I have into 0. How will I make it arbitrarily 0? All I need to do in the number line, whatever the value here, change its sign and add it. That is shifting the axis. If I do that, I add plus 4.5 here, here also plus 4.5, this becomes 0, this will become some positive number. Earlier 0 was in the top, now 0 is here. So, it is in the middle, negative goes below. Now, this I can use to tell, because the Fermi level is here for this fellow and its work function is smaller compared to this guy, because now the vacuum will get a value of 4.5 electron volt, correct? Earlier it was 0. Now, because I added this, so that becomes 4.5. The maximum point here is 4.5. Correct, no? So, now what happens, because this fellow has got less work function than this guy, in the electrochemical series, if you compare these two, the most electronegative element is hydrogen, correct? Or in other words, put it differently, the most reactive metal here is lithium. So, lithium is electropositive compared to hydrogen, correct, no? So, which is more electropositive? Lithium is more electropositive than hydrogen. Now, in the same scale, if you do, your zinc will come somewhere, this is energy, no? Okay, let us now convert to potential scale. If I convert to potential scale, because all of them is a 1 electron process, okay, so I am going to convert energy into potential. So, N is 1 electron, so I have to divide by F, that Faraday constant, whatever it is. So, for 1 mole of species, when I talk about, then you will get the same value with the sign only changed. So, now you see this 0 volt, this is 3.2 volt, correct, no? So, now they look at it, 0 volt here, minus 3.2 volt here, and from this we know this is more electropositive than this. Then what is the conclusion I get? The one interface which has most negative potential is the highest electropositive in nature. The metal electrolyte interface has got the most negative value of potential is most reactive or more reducing agent, right? That is a very good reducing agent. More negative reduction potential, we are talking reduction potential, more negative reduction potential, okay, that is a very good reducing agent. That means in this table, whatever appears here are good reducing agent compared to hydrogen. Whatever appears here are good oxidizing agent compared to hydrogen. We can say with respect to hydrogen which are reducing agent, with respect to hydrogen which are oxidizing agent. Possible, no? So, that is what done. This was done using simple Born-Haber cycle. We did not do any electrochemistry, because by then we know all the thermodynamics quantity, enthalpy of various processes. Here I have not included, see, do not take it like a sacrosanct, because I have not included the entropy components here. So, I have done only an order of magnitude calculation to show you how this is done, okay. So, now if you look at it, without doing electrochemistry, just using the thermodynamics data, people have done this. They have made an electrochemical series which we use it. And this is very clear, this electrochemical series puts the values only in the standard condition. So, if you go to a non-standard condition, you change the pressure, you change the concentration of the solution, something like that, you have to find out the new potential correspond to that non-standard condition using the Nernst equation. Because Nernst equation has got E naught and a concentration term. So, you change the concentration, find out what is our new E. That new E is your reduction potential. So, that new E can be such that depending on the extent of changes you introduced in your system can make what was electropositive compared to hydrogen can now become electronegative compared to hydrogen. That depends on what changes you made in the solution. Correct, no?
Yes, sir.
Makes sense?
Yes, sir.
Any questions? No question? Now, I have a reaction where A goes to B. How do you write the rate of the reaction? Again, you will study in the +2. So, all we know is So, if you see what all we know about this reaction, the concentration of A will be keep on decreasing with the time. But what we do not know is how it will decrease with the time. Will it linearly decrease, non-linearly decrease, exponentially decrease? That is where the order of the reaction comes into picture. So, for that you should know what is the order of the reaction. By just writing any reaction, you cannot find out the order. That is an experimental quantity. You have to actually do the reaction in a given set of condition in order to find what is the order involved in the reaction. So, now most of the electrochemical reaction is all first order or quasi zero order type of reactions. Okay. So, I have taken a reaction, assumed that it is first order. Now, I am going to write rate of this reaction. How do you write rate of the reaction? No, it is exponential decay of A with time. Zeroth order will be linear.
What does the first order mean?
First order, what does it mean? It is the number of species which is involved, okay, in the rate determining step. If you do a reaction, as I write A goes to B, not necessarily A directly goes to B. A may be going to an intermediate. That intermediate may be again reacting with A and then finally giving B. Okay. So, what I have written is a very simple, but actual reaction may be happening at multiple steps. So, in the multiple steps, one step will be the slowest step, and that step is a bottleneck for the entire reaction, and that reaction is called rate determining step, RDS. In the rate determining steps, how many A is involved? If it is 1 A involved, then it is a first order with respect to A. If in the rate determining step, if 2 A's are involved, with respect to A. If you have a reaction A plus B gives a C, then rate depends on both A and B. Then in the rate determining step, if 1 A and 1 B is involved, the total order is second order, but first order with respect to A and first order with respect to B. Understand? So, that you will study anyway. So, now what is the reaction dA by dt, t here time, how A changes with the time, it decreases with the time. So, minus dA by dt is, it is involved with some rate constant K times the concentration of A, okay, concentration of A. Since it is a first order reaction, power is 1. If it is a zero order reaction, power is 0. If power is 0, then dA by dt will be equal to K. It is a constant, right? Yeah, dA by dt equal to K, the K can be a negative value, right? Mathematically we can say that. So, then what it means for a zero order reaction, rate is constant. Since rate is constant, it is like y is equal to mx. It is going to be linearly decreasing A with time. But for first order reaction, what you have to do? Integrate. Then you finally go to the answer, solve the problem, you will get an exponential function. Okay? I am not doing that because I am not here to do that. I only do electrochemistry. Okay? You please do it. Okay? Now this is a rate. Okay? What is the unit? A is the unit of concentration now, bracket A, right? So there is moles per centimeter cube and dt is seconds. So moles per centimeter cube per second. So how many moles of A converted to B in this case in a unit volume centimeter cube in every second? That is the rate of this particular reaction. Yes or no? That means what? I am talking about a volume in which reaction happening. So it must be a homogeneous reaction. Why? Because in every volume I take in that given trough, okay, same reactions is happening to the same extent, correct? So it is a homogeneous reaction. What if it is a heterogeneous reaction? Heterogeneous means what? There are two phases involved. At the interface only reaction happens, like electrochemistry. In electrochemistry, we have an electrode and there is an electrolyte. Reaction happens at the interface of electrode and electrolyte. Often these two are two different phases. Often these two are two different phases, correct? You have what? An electrode which is usually solid. It can be liquid sometimes like mercury. And then you have an electrolyte which is a liquid phase and these two are not miscible. So at the boundary only reaction can happen. That's a heterogeneous reaction. Heterogeneous reaction, rate constant K, here rate constant is second inverse. In heterogeneous case, it is centimeter per second. So the rate of the reaction for heterogeneous case rate of the reaction R equal to in the unit mole per centimeter square per second. That's the unit. R will be in this unit. Okay? Moles per centimeter square per second.
So is the reason why it's centimeter square because heterogeneous reactions only happen over the surface?
Yes. How many moles converted of A converted to B in a unit area in every second? To get that unit, then your rate constant has to be in the unit centimeter per second. Order is same, first order. It is only the type of reaction is different from homogeneous to heterogeneous. So if someone asks what is the unit of rate constant for a first order reaction, if you say a second inverse, as per your textbook you are right. But people like me who comes and knows all these subjects together, heterogeneous, homogeneous, will say no, be more precise. Because your answer is one possibility. You are assuming I am asking for homogeneous. That's because that's what is in your textbook. But I would have probably meant heterogeneous because I am electrochemist. You understand, no? So, yeah, fine. Any other question? Involved during rate determining step.
Then how do we have negative orders?
Negative orders means something poisoning your reaction. Studying further.
Sir, you said order of the reaction.
But where you have negative order? In which reaction? No, they might mean something different. But negative order means what? You are retarding a reaction. So mere presence of something is retarding a reaction, right? I don't think so. We are discussing that here.
Sir, you said order of the reaction is experimentally found out.
Yes, count quantity.
How can you experimentally find out the number of molecules?
There will be some spectroscopy techniques. There will be some techniques with which we have to do some mechanistic investigations of your reaction, which you are not doing. In a very simple case, let me tell you like this. Very simple case, which is what there in your textbook. See, rate of a reaction. Okay. Now I am doing this. So this is a concentration of A, this is concentration of B, this is a rate. Okay. So I have initially one of this, I have a rate some value, say 6, some value arbitrary. You have to put units, I am not putting. Suppose in the reaction mixture, you are going to add 2 moles of B and you are seeing somehow, you have a method to see. Rate of the reaction doubles. So basically what you need to do is you have to keep changing, keep one of them constant, keep the other one vary, keep this or keep this constant, this one vary, and see what is the relation between this and this. If I double this concentration, if the rate goes 4 times, it means it has some square here, right? If I double this constant, rate goes only 2 times, it means it's only 1. That means order is 1 with respect to this. So you can do these kind of experiments that will come in the coming year. So to identify the order with respect to A, order with respect to B. But actually how it is done in the laboratory, you must have some tools, analytical tools to do this. You have to have a way of measuring concentration, or you should have a way of measuring rate, something must be there. So you can do that. In electrochemistry, if you ask me, very simple, because I have an ammeter that directly displays me the rate. Why ammeter directly displays the rate? So if I take this rate what I have written here, you multiply with N and F, what you get is current density. Correct, no? If I multiply by N and F, you will get current density. How? You just calculate. F is coulombs per mole, and the rate there is a mole cancels, and then N is a number of, is a stoichiometric coefficient, number of electron involved in that. So mole got cancelled. What you are left with the coulombs per second, that is ampere, then centimeter squared, ampere per centimeter squared. That's current density which is directly displayed by ammeter. So now imagine I have a reaction wherein this is an electrochemical reaction where I suddenly double this and I find my ammeter suddenly showing double the rate, double the current. That's one way. Electrochemically I can do it like that. Like that, you will, depending upon the reaction, we will have some tools. That's beyond the scope of discussion here, but you will find it. You will do in the laboratory also some experiment like that.
Sir, ammeter is just showing current, right? Not current density.
You know the electrode area, right? Okay, certain things implicit, right? You know, you only made that cell, so you know the area of the electrode. Correct? Right now? Clear? Any question? So now if you see what is a rate in kinetics, I can convert into current density in electrochemistry. And what is delta G in your thermodynamics, I can convert that into E cell. So instead of talking about delta G, electrochemistry will talk about voltage, E cell. Instead of talking about rate of the reaction, electrochemistry will talk about current. So only these two we talk about and make a subject called electrochemistry. It depends. If you don't multiply by area, you will get current in ampere. If I don't put area there, you will get current in the the I in the unit of current density, ampere per centimeter square. Yeah, it depends. Now the way I have written right now, it comes in the unit of ampere per centimeter square. If you multiply by area, you will get in the unit of ampere. In fact, your ammeter tells you only ampere, not ampere per centimeter square. But we know because we know the area of the electrode. We can divide that by centimeter square, total area of the electrode, that tells you. Ammeter reading divided by the total area of the electrode tells you what is the current density. Right now? Any other question? No question? So now we understood the rate of the reaction, what you call in kinetics is now we have started calling as current density or current, okay. And you also now understood what is the, what is the order of the reaction, how the order comes out. It is an experimental quantity coming from the actual experiment that you perform. You have to probe that experiment and then understand what is the order of the reaction. And mostly electrochemical reactions are quasi-zero order or first order reaction. So I just straight away went to a first order example in this case. Okay. Now, see, I don't want to use this place as an extended classroom for you. You are here to know something beyond textbook. Okay, so tomorrow's class will be on the batteries. Okay, using this whatever we learned today in fundamentals. You understand, no? So if I am teaching the same thing in the class book, why will I do that? I don't do that. Okay. Now, what is happening? Now you understood bits and pieces here and there because some of the things you had to study, crystal field theory, and what are the rate of the reaction, all that. But I hope you have some idea before even that is started in the school. Okay. So some of you may be going for coaching centers, right? Alan or anybody going here? How many of you going to some coaching center? If you are raising half hand means what? You will start from home but you will not reach there? This many going, no? Then already they would have entered into +2 syllabus, right? Because you are the vacation of +1. Fiji?
Fiji shut down, sir.
It doesn't matter. See, it is like a first law of thermodynamics. Energy can be changed from one form to other form, cannot be killed. Fiji guys would have joined Alan now. That's all, no? Akash, whatever it is. But the same guys. Right, no? So they are all the same fellows. Now, let's do this. What I was thinking to do now, delta G is done. Okay. So now, you might have read something called activation energy in kinetics. Okay. So especially those who are already started coaching and all might have heard this term activation energy. And I don't like that term. So electrochemistry use again different word. We use something called over potential. Okay. Over potential. What is over potential? It is more than what is required is called over. Over and above what is required is called over potential. Right? So now, so now I have a reactant. So I have a product and this guy is supposed to go like this, which we know. This is energy and this is your reaction coordinate. Correct? Now, in regular chemical kinetics, how will you manipulate this gap? That's activation energy, right? How will you manipulate that gap? So far, what is the problem? What's the problem being exothermic reaction? Oh, you are asking for that. Okay. Change the temperature, you can manipulate the gap. Manipulate the gap means it can increase also, decrease also, right? How will you affect the gap? Catalyst. Suppose I want catalyst is generally used for the positive result. That means we want to speed up the reaction in a given direction, what you want, right? So the catalyst, if you put what basically catalyst does, catalyst gives you a new path by which the reactant goes to product. This new path happens to be a smaller activation energy. Therefore, the reaction happens faster. See, the problem with the thermodynamics, it tells you this can happen, but it will not tell you when it will happen. It's like a father. My daughter will ask, I want this. Okay, I will say. She will come next day, where is it? I said, okay. I never said when I will give you. You understand, no? You have to wait. You have to have patience. Next day she will ask, I say, yes, I am busy today, I will do tomorrow. Tomorrow she will come and say, yes. Don't come tomorrow means tomorrow. Tomorrow means future. Go. Like that, it will go like after 1 year. Right, no? Then we will say, okay, now he has waited enough, we will give now. Correct, no? It's like that. Thermodynamics is like that. It's a father. It will tell you, yes, it will happen. Never tell you when it will happen. Okay? But kinetics is not like that. Kinetics will tell you when it will happen. Okay? Correct, no? That's the kinetics. So delta G less than 0 does not guarantee that you will see the product in real time. Hydrogen plus oxygen in standard condition gives you water for that delta G is less than 0. Take hydrogen and oxygen, put it in a box and keep waiting, you will not see water. You come, take several bursts and come back also, you will not see water. That is that slow. The reaction is that slow, but delta G is negative. What it means? For that reaction, activation energy is so humongous that it's very, very rare one hydrogen and oxygen collide and form a product H2O. Takes time. But you just insert a platinum there in that mixture, you will immediately see water forming. Because the platinum gives a surface wherein both hydrogen and oxygen can absorb, comfortably react, produce water. So that is giving an alternative pathway for these guys to meet. Understand? No? Yes or no? That is what catalysts do. So, but in electrochemistry it is very interesting. Basically what happened, when you add a catalyst, the rate of the reaction correspond to this plot and rate of the reaction correspond to this plot. If you look at it, R2 is greater than R1, correct? Rate of the reaction. EA is lesser, but R2 is greater. So the same effect without using catalyst, I can bring it in electrochemistry. Right? So you have an electrode-electrolyte interface. This was a Fermi level of your electrode, and this was the redox energy level of your electrolyte. The moment you put metal into the electrolyte, there is a Fermi level equilibration. Therefore, the electron jumped out from here, and then it gained positive charge. This gained some negative charge. So now a new level is produced. Okay. Once this new level is produced, the number of, if this reaction is A goes to B, the number of A goes to B as well as B goes to A become equal. So at this point in time, in this condition, you have a perfect equilibrium. And each electrode-electrolyte interface, that means half cell. Now imagine, I am somehow bringing electron from somewhere and added to that electrode. Then this equilibrium, now I am again lifting. If I do that, what electrode will do? It will spend that electron. How it will spend the electron? It will give to the electrolyte again. So now I take my equilibrium here, then again the electron will flow from here, this level will shift up. Correct?
Sir, won't that energy level decrease?
Which energy level?
That should also decrease, right?
It decrease. I put it here so that come here.
Oh, okay.
Now again add electron, take it up here, again it will go here.
Oh, so this is like recharge.
Same. So now what is happening? The concentration in the solution side is continuously changing. Because I am changing the level means what? I am changing the concentration here. Correct? But I brought electron from somewhere, added to this electrode. That's how I could do this. That means I did some reduction reaction here. So I brought some electron from somewhere, added to that electrode, arbitrarily changed the Fermi level of my electrode. Therefore, there is a reduction, electrolyte, something in the electrolyte got reduced. So the concentration of the electrolytes keep changing. As long as I add electron, it will be keep changing. Make sense? Now do the opposite. I remove the electron from the metal. Already metal is lean in electron because it gave some electron to the solution, positive charge this side, solution side negative charge. Now I remove some more electron forcibly. Then what will happen? Electrolyte will give the electron back. Then again I remove some electron forcibly. So more electrolyte will give electron now. So the concentration of the electrolyte again will change in the other direction. Clear? So this adding the electron or subtracting the electron from the electrode is called applying potential. If someone says I apply potential, what I am doing basically is I have given electron to that particular electrode, I removed electron from there. Yes, I am creating a gradient. Correct? Potential gradient across the interface I am creating. Therefore, I can force charge one or the other way depending upon how I create the gradient. Correct, no? Make sense? So, this is what I said. Now, by adding electron or removing electron, what I manipulate is the rate of the reaction.
Yes, sir.
Earlier, there was no reaction at all, it was at equilibrium. By just adding some electron, I made the reaction to happen. Adding more electron, I made more reaction to happen. That means I am manipulating the rate of the reaction by way of adding the different quantum of electron in a given time. Different quantum of electron in a given time means different current. I is different.
Yes, sir. Yes, sir.
So if I manipulate the I that is flowing through the electrode, I manipulate the rate of the reaction that happens at the interface. something that changes the rate of the reaction we call catalyst. But here without adding catalyst, I manipulate the rate of the reaction. Somebody sleeping? Okay, that's background. See, is right? Without adding catalyst, I have made the reaction rate to vary. Correct or not? So this is like the potential which you cannot see is a catalyst now. It's a software catalyst, isn't it? Catalyst is generally hardware, right? No, you have a software. It is like your mind. You think positively, you achieve. You think negative, you achieve something else, which is not desired product. Always there is a product for what you do. That product may be liked by the others, may be disliked by others, depending on whether you think, whether you thought progressively or another way. Correct? No? So you always generate a product which either society wants or disowns. Keep that in mind. So you have a catalyst in you, that is your thinking, your way of orienting yourself. That you make it for your own use, then you are escaped, problem solved. If someone achieves something, don't get angry. You aspire, you also should achieve that. That's the best way. If you get angry, you can't stop that person because you are not in equilibrium with that person. Anything happens in you does not affect the other person. You understand? By getting angry, he cannot stop his performance. You have to perform independently so that the same feeling now generated here. That is the only way by which you can do. But if he is a good guy, you will not get that feeling generated. You understand, no? Right. Philosophy is enough. Now you see, without using catalyst, we have done different rate. That's the beauty of electrochemistry. If it is a galvanic cell, how will I change the current flowing in the circuit? In a galvanic cell? Power potential we are going to discuss. How we change the, if you are doing an experiment, the magnitude of the resistor you have to change. By changing that, rate of the reaction can be controlled. If it is an electrolytic reaction, how will you control the rate? You have to have a power source to do here because power you have to give. So you have to use a power source, it will set different potential at the electrode with respect to your reference. You have to do. Okay? This is how you do electrochemistry, very simple. Right? So in your cell phone, you do more work, it means you are reducing the resistance in the for the battery so low that more work you are parallelly doing. If you are not doing more work, that means you are charging your phone, keeping it idle. So very big resistance is there, small current flowing just to keep the battery alive, phone alive. When you do action, you are basically reducing the resistance, external resistance. So more current flows and more work is being done by you. Okay, right. Clear? Any question? Now over potential. What is over potential? What I have done at the interface, so this probably the situation at equilibrium. Okay, that means you have a metal, you put in the electrolyte, this was a situation at equilibrium, it looks like this. So I have not drawn to scale, but imagine, so this slope is different from this slope, therefore the rate at which R goes to P or P goes to R are equal now. Okay, so further you have to manipulate the slope. Climbing a mountain which is steep is difficult, right? Climbing a mountain is shallow, is almost like a flat. So the slope actually influences the rate of the reaction. So that's called potential energy slope for a reaction. So now you see, if the R goes to P, P goes to R same here, that means the system is at equilibrium now. Okay, number of R goes to P, number of P goes to R in a given time is equal. Now I am going to apply over potential such that I want more P. So which way I should shift R? If I shift R like that, then how will I shift R here? Basically the energy level of R has changed. How would I change the energy level of R? Because your R is in contact with your electrode. So I add something to your electrode. What is that something? Electron. Or remove from the electrode. Because R to P I have not told you whether it is oxidation reaction, reduction reaction. So here it is a direction, I am not worried about it. I am only worried that R goes to P. If R goes to P means activation energy has to be reduced. if R goes to P is an oxidation reaction, then I have to remove the electron so that easily I will convert R to P, because I create a gradient, so R loses electron. So that you have done, but here we are generalizing. R we don't know is oxidized species or reduced species, P we don't know it's oxidized or reduced, we only know R goes to P. So for this generalized pattern, I know in general I have to reduce the activation energy for this process. How will I manipulate the the energy of the reactant? Because it is in contact with the electrode, if I manipulate the energy of my electrode, energy of the reactant will be manipulated. How will I manipulate the energy of my electrode? I will add electron. If I add electron, energy of the electrode will increase, because available orbital, empty orbital will now receive electrons, so the topmost level will be at higher energy. So if I remove electron from the electrode, then the energy of the electrode will decrease. If energy of the electrode decrease, it may receive electron from the electrolyte. Okay. So now something I am doing such that I want R goes to P. So I applied now what? A potential to the electrode. That means I added or removed electron to the electrode. So therefore the R now changes its position. When R changes, automatically activation energy will change. But the beauty in the chemical kinetics is, if I change this much the energy level of R, not necessary activation energy also will change that much proportionally. That is kinetics. Thermodynamics, you have laws to say what it is. In kinetics, every time you do an experiment and calculate what is activation energy. Every time you do an experiment and calculate what is the rate of the reaction. This is something you cannot predict upfront. What's the reason for the change? Because when I change the energy level of R, it is no longer the same R. It's a different R. So its reactivity or the mechanism it follows to produce P can be different. That means it may produce still P not by the same route. It's like you see a mountain, you want to go to the other side of the mountain. One way is you climb hard, go up and come down. Other way is go around the mountain. It's left to you. Okay. So this is what happens. What profile it will choose, it is left to the reaction which you cannot say. Therefore, I am not able to tell you in advance whether it will move the same magnitude. It may not. That's what the experience is. Okay. So you can see this may be going somewhat like this. There is this much increase in energy, but it's only this much increase in the activation energy. But the net, there is a decrease in the activation energy in this process. Correct? Therefore, the rate of the reaction goes up. Okay. So there is a link between the rate of the reaction and the activation energy. That is linked again to the energy, the magnitude of energy which I have changed. The magnitude of energy which I have changed is called over energy. Okay. Energy I can convert into potential. How will I do that? If I convert this difference in energy, our potential is in the unit of volt, multiplied by N and F, charge into voltage, that is energy, correct? So I can represent this excess energy I spent in terms of over potential, because I know what is N, what is F. So I just multiply by that I can. So this excess energy which I spent in order to speed up the reaction is called over potential, and that much energy you have to spend. It is subtracted from the available energy. What was available energy? This was the available energy, correct? From there you subtract. Correct? No? So it is always a penalty. Over potential is like always a penalty. Whether you do electrolysis process or galvanic process, always there is a over potential, because always there is a reaction involved. Always there is a resistance for the flow of charge. That's why there is over potential. Okay. So therefore this over potential is like a penalty. So you need to construct a system wherein the over potential is minimum. Since it is not a full length electrochemistry course and it is not needed for you at this stage, I can tell you few origins of the over potential. Okay. Where and all you have to spend excess energy in order to make a reaction happen qualitatively. How? For example, I have constructed an electrolyte, a cell with one side hydrogen electrode, other side chlorine electrode. One side hydrogen electrode, other side I have an electrolyte, say 1 molar HCl, say 10 molar HCl, say 20 molar HCl. possible. Now, will the rate of the reaction, and I put the same resistor outside, same resistor, and put a ammeter to measure the current that is flowing. Do you think the current will be the same in all the three cases? Why? Different in the solution. That means its conductivity will be different, its viscosity will be different, right? No? So, what that conductivity and viscosity affect? It affects the rate at which ion move in the solution. So, that means the resistance for the flow of ion has been manipulated. So, that is a source of overpotential. So, depending upon the extent of conductivity of your electrolyte, overpotential can be higher or lower. If lower the conductivity, higher the overpotential. That means you have to spend energy to pull the ion. If electrolyte is better conducting, very good conductor, then overpotential associated in moving the ion will be smaller. Correct? That is one. Other one that we will do tomorrow, that's called lithium intercalation, deintercalation. Suppose imagine you are doing the same reaction in a solid state. So, you are creating something, oxidizing something, reducing, but in solid state. So, in the solid state, something oxidizing, reducing means you are added electron, removed electron. That means size of the ion will be changing. Correct? No? The solid state. Imagine whatever the reaction you did, imagine you are doing it in a solid state. Okay? Hydrochloric acid solid. Yeah, it is all advanced concept. We will not get into that. Now, I want you to understand the origins of the overpotential. It is there not just in lithium polymer battery, in any battery, any device, it is there. But what we need to understand is a hypothetical experiment where hydrogen electrode is solid, chlorine electrode is solid, in hydrochloric acid solid. See, may not be possible, but say hypothetical. In that condition, what will happen? When you are oxidizing hydrogen, you will produce proton. That hydrogen disappeared, become proton. That space now become vacant. Now this proton has to move through the electrolyte, which is again solid. So it will be hopping like that. Then it will go to the other side where the chlorine become chloride and takes the H plus become hydrochloride. Hydrochloride is slightly bigger than chlorine, so it need more space there. So in one side the space is created, that means hydrogen left. In the other space there is a demand for the space because you produce a new species which is still there. So in one phase you have to shrink the volume, the other place you have to increase the volume. So that means you are basically moving the atoms. To move the atoms you have to spend energy, right? Nothing moves without a force. Force is energy, right? So you are spending energy to do these atom movements. So whenever these kind of displacement of atoms, things like that, bond cutting, bond forming happens, then you spend energy. That is one place where you spend energy, penalty, overpotential. So there is overpotential for the movement of the ion, there is overpotential for the breathing of your electrode, change in volume, right? And there is overpotential for the reaction itself because the electron to transfer itself is not straightforward. It has to go through an activation process. So that's called activation overpotential. Energy that is lost in activating a process is activation overpotential. Energy lost in transporting ion is ionic ohmic overpotential. Okay, it's a resistance, ohmic resistance, right? So like that there are various type of overpotentials that are there. And all the penalty you have to pay and the remaining energy is what you can use. That is delta G. Okay, so that is a useful energy that you will get to finally after subtracting all these overpotentials, right? So if you understand now, so these are the origins. So overpotential in simple terms, it's a penalty. In other words, very simple analogy if you want to do, suppose I have water in the sump, I want to take the water up there. So what is the energy required to do this process? All you need to do is find out the potential energy of that, potential energy of this, subtract, it will tell you how much energy required. Can you do it within that energy? Can you? You have water in the sump, you want to take the water to up. I want you to calculate before doing that experiment how much energy required to push this water from here to there. Equal will never happen. It's out of question. That is theoretically. Experimentally, equal not possible. Always at least a delta greater than has to be there. Why that delta then? Because it's only this much required. No, we give only that.
Sir, we are considering only ideal scenario while calculating.
See, in thermodynamics, there is something called state function and path function. You are only calculating state function and you are saying this is the energy required to go there. But actually what happens, you are not worried about how are you taking from here to there and inefficiencies involved in those. So when you are pumping, you don't have an electrical pump which is 100% efficient. When you are pumping, you don't have a tube which does not have friction. Correct? No? Done. So you don't have a friction-free pumps, you don't have a 100% efficient pumps, you don't have a friction-free tubes, correct?
Yes.
So because of this, you have to add little more energy to take care of these inefficiencies. Therefore, in practical, it will spend more energy. Otherwise, you would have spent your electricity bill would have been smaller. Now it is bigger. That difference between the actual electrical bill you supposed to have gotten and what you have paid, that difference is called penalty. That is overpotential. Right? Same thing while discharging the solution also. You can expect a flow rate, but if the flow rate will be less than that flow rate. Why? Because the solution is touching the walls and flowing, there is a friction. It may be very small, but still there is a difference. Right? So therefore, you are not getting the water at the output you want. It's giving slightly lesser than that output. And practically, we will correct for all those things, designing all the different, but there is a penalty. Right? So this is our potential. Okay, so I will stop here. Tomorrow we will do a little bit on lithium battery. Close.
Shri Gurubhyo Namaha. It's my honor to deliver the formal vote of thanks to express our immense gratitude to Professor R. Kothandaraman for a truly insightful and engaging lecture. Your clarity and depth of knowledge have given us a fresh perspective on electrochemistry, and your witty examples have done very much to liven up the subject. Thank you, sir, for taking the time to share your knowledge with us.
Swayam Prabha. Digital India. Educated India.